In this lesson, we start the discussion with a recap on the concept of stationarity. We discuss the types of non-stationarity and how to resolve each of these types, namely stochastic non-stationarity and non-stationarity with deterministic trend. We also discuss the visual examination of security prices corresponding to different ARIMA processes. And we also visualize different kinds of non-stationarities and the differences across these processes. Next, we discuss the unit root test and test of stationarity, including ADF, that is augmented decay Fuller, PP test, and KPSS test. Lastly, we discuss the concept of co-integration, mean reversion, and error correction models. We also discuss the Engel-Granger two-step approach to ECM and co-integration. In this video, we'll recap our understanding of time series stationarity. We'll also discuss some of the problems associated with dealing and modeling non-stationary series. Recall, in our earlier discussion, we said a strictly stationary process is a time series process yt when we pick a set of sequence, let's say yt1 to ytn, and the joint distribution of these observations remains same whether we pick another sequence from yt1 plus m to ytn plus m. And similarly, we can move and take any such sequence, and if the joint probability, and this f is notation for joint probability distribution, if it remains same for yt1 to ytn, a sequence of n terms, to yt1 plus m to ytn plus m, then this series is said to be strictly stationary. But this strict stationarity condition is a rather stringent one and less practical. So in a practical sense, we make use of what we call as weakly stationary process. What is weakly stationary process or covariance stationary process? If you recall, we said that it's a process for which the mean of the distribution is constant over time, its variance is constant, as well as the autocovariance is also constant. So it does not matter in the sequence which T1, T2 or Tn we are looking at. What matters is what is the difference between this T1 and T2. So for example, if you are looking at two sequences, let's say T1 to T5, their autocovariance will be same as T2 to T6. So what matters is not at what time they are, only their difference, and you can identify what would be the correlation. So rather, in simple terms, we are saying a weakly stationary process is a process where the process mean or expected value of the process, its variance, which is the second moment, and autocorrelation structure or autocovariance remain constant across time. We also noted that it is difficult to make sense or make a lot of use of the autocovariance, which is this expression, expectation of yt minus mu, which is the mu is nothing but expected value of yt itself, and similarly yt plus s. This expression is autocovariance, but because of scale thing, this autocovariance is not very difficult to make sense. It's slightly difficult to understand, and therefore what we do is we compute something called autocorrelation by dividing this autocovariance with the variance term. What is variance? Variance is the autocovariance of yt with its own self, with its own term, neither lead nor lag, same. So this tau s is the autocorrelation. It is given that obviously if when lag is equal to 0, then autocorrelation will be 1, because we are computing correlation of yt with its own self, and for all the other lags it will lie between +1 and -1. So this is called autocorrelation, which is a slightly more reformed measure of autocovariance. Now let's discuss some of the problems with time series stationarity. In a practical sense, when you have two random series, let's say yt and xt, which are purely random with no connection with each other, when you'll try to compute correlation or regression between them or any such statistical relationship, it should be 0, right? However, when you run the regression of these two yt and xt, even though they are random, but if they are non-stationary and you sample, let's say you sample certain time periods for this process, let's say t1 to tn or tn plus 1 to tm, and the series are stationary across different samples, you plot t statistic or adjusted R square stats, which exactly a measure of the relationship, statistical strength of this relationship. You'll find a rather high value of adjusted R square. Ideally, it should have been very small, maybe even 0. But when you sample these process maybe 1000 times or 500 times and plot them, this kind of adjusted R square measure will appear. In fact, many times it is even more than 50%, that is 0.5. Similarly, in a strict theoretical sense, the t statistic from the regression should follow t distribution, which means almost 95% of the observations, 95% of the observations should lie between plus minus 2, close to plus minus 2. However, this kind of t statistics appears where the large number of values are beyond that plus minus 2 range. In fact, a lot of them, even more than 90%, which indicates this is regression is rather spurious. That means our results are not correct, and this is ascribed to non-stationarity property. So to conclude, we saw that in practice we rather follow a weak stationarity condition, that is the mean, variance and autocovariance structure should remain constant, and if our series is non-stationary and we do not do anything about it, our regression or any such measure of statistical strength is spurious in nature. In this video, we'll discuss the two key types of non-stationarity and their key characteristics. Let us introduce the two key types of non-stationarity in financial econometrics. The two key important non-stationary are random walk model with drift. This is also called stochastic non-stationarity. It appears like this process yt equal to mu. Mu is the drift plus yt minus 1 plus the error term mu t. Now this mu is the drift and yt minus 1 comes with a correlation of 1. We'll have a more detailed discussion in later subsequent slides and videos, but please notice the coefficient 1 has the implication that any shock to this series, historical shocks to the series, do not die away. We'll elaborate this in more detail. And that is why this is called stochastic non-stationarity. How to deal with it, what is the nature of this kind of non-stationarity, we'll discuss shortly. Mu t is the error term, which is often considered to be a white noise IID process, as we discussed earlier. That means identically and independently distributed, and that identical distribution is often considered to be as normal. So this notation is for a normal distribution with zero mean and constant variance, and this is ascribed to this white noise mu t process. The second non-stationarity is called deterministic trend process or trending process. It appears like yt equal to alpha plus beta t plus mu t. The non-stationarity comes because of this part. The violation in non-stationarity comes because of this part, because of this trending time term. The mean and other things are not constant over time. So if you recall, in the weak stationarity, we assumed a constant mean of the process, variance and auto correlation structure. Because of this time trend, those terms are changing with time, and therefore this is deterministic trend process with non-stationarity component. Now, how to deal with these non-stationarities, we'll discuss in subsequent videos, but one important concept we'll again recap: the white noise ID process. So if you recall, a white noise process is a process with no discernible structure. In financial econometrics, we generally assume that the mean of this process is zero. If you recall our previous discussion, particularly for security market returns, this is a very good assumption, because it is difficult to believe that any particular stock will give you abnormal returns in some kind of this mean which is greater than zero, or if it is less than zero, then opposite argument can be applied with short sale logic. That means you will sell the stock short. Also, for this white noise ID process, we said that its variance is constant, and because there is no deterministic structure, its autocorrelation structure is zero. There is no autocovariance, there is no discernible pattern for all the t's which are not same. So this white noise process has a zero mean, finite constant variance and uncorrelated across time. We also put a normality assumption, which is a good assumption to follow. Now, why this white noise ID modeling need for the error term mu t? The idea here is that when you model a process yt, maybe some kind of ARIMA model, and then you extract the residuals from the model. We assume that if the modeling has been good, then the residuals should be very clean. They should not have any pattern or some kind of structure that requires modeling. And therefore, when we are doing the model diagnostics, it is rather more residual diagnostic, wherein we extract the residual. The assumption is that these residuals are theoretically should be white noise ID process, and if they deviate from a white noise process, that means we find some kind of autocorrelation structure or some modeling possibility, some systematic pattern in this error term. Our residual diagnostics or model diagnostics suggest that our modeling is not very adequate and efficient, and we need to put some more efforts in modeling our YT. So the criteria of a good model in terms of modeling YT time series is that the residual should be error free when we perform the residual diagnostics. They should have no discernible structure. There should not be any systematic pattern in this mu t. It should be a white noise process. That is what we assume. So to summarize, in this video we saw the types of non-stationarity, which is one is time series or deterministic non-stationarity, and another is the stochastic non-stationarity. In subsequent videos, we'll see how to tackle with these form of non-stationarities. In this video, we'll discuss stochastic non-stationarity and how to account for it while modeling the data. Think of a generalized AR autoregressive AR1 process like this. Yt equal to mu plus phi t minus 1 plus mu t. Mu here represents the drift and yt minus 1 is the autoregressive term with its coefficient phi. Now, what would happen if phi greater than 1? This would become an explosive process because each of the previous term has an accumulative impact which is increasing. For example, the impact of yt minus 1, let's say a shock came at time t minus 1, which is mu t minus 1. The impact of the shock on next period yt is a multiple of phi. In the next period, phi square. As long as this phi is greater than 1, the impact of the shock on the process will explode, which is not a very desirable property and a property which does not describe the real economic and finance data. So generally we tend to ignore this part. However, there is a case for phi equal to 1. There are periods of extreme turbulence such as COVID period or similar crisis periods where this phi becomes equal to 1. What is the implication of this? The implication is that if there was a shock in t minus 1, which is mu t minus 1, this shock in future periods will not die down. It will keep on multiplying phi to the power 1, 2, 3. And if phi equal to 1, this shock will not go away and mu t minus 1 will always persist in the series. So this kind of non-stationarity has been found to exist. Let's see more mathematically how it works. Let us recall our generic case of this AR1 process. For time being, we'll assume that drift to be 0. As we said, we can assume that drift to be 0 for ease of modeling. Now, if we look at the term yt minus 1 in a similar vein, we'll subtract 1 from the subscripts to get this kind of expression, that is yt minus 1 in terms of yt minus 2 and yt minus 2 in terms of yt minus 3. Now, let us try to express yt in terms of its lag. So, if we can substitute instead of yt minus 1, we can substitute this expression to get yt in the form of yt minus 2. And here, as you will see, this term will become phi square yt minus 2. Now, for this yt minus 2, we can also go further back to express this in terms of yt minus 3, and then the term will be yt cube and so on up till, let's say, the first point is phi t, which is the first term as y naught. So let's say first the series originated at y naught and the corresponding time period was t. So this phi to the power t, y naught is the first term, yt, and then subsequent terms will be in the form of these white noise processes, mu t minus 1, mu t minus 2 and so on. Now, a very interesting thing is happening here. If this phi is greater than 1, like we said, the shock will, none of these shocks will die away. Even till mu naught, the shock will explode in fact. However, if this phi equal to 1, it has a very undesirable property, whether this is a more recent shock or a shock which was much further away in time, that is mu naught, this will also become 1. So mu naught or mu t minus 1, mu t minus 2, whatever shock exists, it never dies down. However, for a financial or economic time series, a desirable property is that such shocks should decline over time. Their impact on the series should decline. However, as long as the value of phi equal to 1, it does not die. Only in the case where this phi is less than 1, in that case, this phi to the power t tends to 0 as t increases, and then only the shocks to the system die away. So a desirable property that these shocks or these coefficients to mu t should be less than 1. In that, or rather in this AR1 process, the phi is the autocorrelation coefficient for the first order process, that is yt minus 1. It should be less than 1. However, as we said, there is a type of data or series that exists where phi equal to 1, often during crisis periods like COVID. In those cases, the shocks persist in the system and never die away. And you have this kind of process, yt equal to phi y naught plus this summation mu t into phi t. And since phi equal to 1, it will be simply the summation of mu t's over time. That means shocks will never die away, no matter how further away in time you are. Let us see how to deal with this kind of non-stationarity. This kind of non-stationarity, this is the generic expression. We have taken the drift also. This is often referred to as random walk non-stationary process or a stochastic stationary process with drift component. This is the drift component. The easiest way to remove this kind of non-stationarity is through taking first differences. What do we mean by this? So we have this yt process. If I take this yt minus 1 on the LHS, we are left with what we call as first difference, which is yt minus 1, which can be written as delta yt. So delta yt is yt minus 1, which is also called first difference. And you recall, we also said that lag operator on yt, which is like L to the power 1 by t, which is nothing but yt minus 1. So in lag notation, this becomes Lyt, or we can make it into the polynomial form if you recall, 1 minus Lyt equal to mu plus mu t. Now this is a stationary process. As you can see here, this is a stationary process. That is, delta yt is a stationary process. So the first differencing has introduced stationarity, and therefore the process is called integrated to order of 1 by, because we only needed to take first difference once. So we only did the first differencing once. So this is called integrated of order 1. If you remember, we said the process is ARIMA, where I is this order of integration. I represents this order of integration. So this is how you deal with this non-stationarity. You account for the non-stationarity by taking first difference. In this case, it is an integrated of order 1. So you have to take only first difference. It could have been second order non-stationarity, then you would have to take the first difference 2 times, and in that case this I value will change from 1 to 2. So depending upon the order of integration, the I value changes, and this is how you account for that non-stationarity. Also, if you recall, this 1 minus L can be written in a polynomial form like 1 minus Z, and this is the characteristic equation of the process, and it has a root at Z equal to 1, and that is why this is also called a unit root process or unit root non-stationarity. So the process, the characteristic equation of the process has a root at Z equal to 1, which also indicates non-stationarity, and that is why this is also called unit root process, because of the existence of this root which is equal to 1, or in technical terms we say that root lies on the unit circle. The root of the process lies on the unit circle. Let us summarize what we discussed in this stochastic non-stationarity. We said that first differencing introduced stationarity in a process that was integrated of order 1 or I1. So if a non-stationary series requires differencing of d times, then it is said to be order of integrated at d. So it is of order d. And it can also be written as yt tilde id. That means it is an integrated process of order d. So the integration is order of d, and it requires differencing d time. That means delta d. This delta d represents d time differencing. When it is applied on yt, it will return an I0 process. That is, if the process yt is differenced d times, it will result in an I0 process. That is a process with stationary. It's a stationary process with no unit roots when difference d time, if the process was integrated of order d. For example, if it is integrated of order 3 times differencing, that means delta 3 times differencing will lead to a I0 process. What is the key difference between these processes that are non-stationary and a stationary process such as I0? So non-stationary processes such as I1 and I2 can wander very long away. For very long times they can wander from their mean, and if there is a drift, then that wandering property will be even higher. In contrast, an I0 process will fluctuate around the mean very swiftly, so it will very frequently cross the mean. If there exists a long-term mean, the I0 process will behave like this. It will cross the mean very swiftly. But if it is I1 or I2 process, it will deviate and drift a lot from the mean. And even if there is a further drift, that mu component is there, then these deviations will be very large in magnitude, and it will remain and so away from mean for very long times. In this video, we'll discuss deterministic non-stationarity and how to tackle it. Recall, we said that deterministic trend process appears like this, where yt is a function of time trend t. Now, this is a rather simple case of non-stationarity, because to deal with it, only what is required is detrending, what is called detrending. So all you need to do is, in the process yt, you model it with the time trend t like this. And once you model out the time trend d here, you will find the coefficient beta and constant term alpha. The residuals from the process mu t will not have time trend. So All the subsequent modeling we can do on mu-t by removing the time trend through this process, and subsequent estimation can be performed on these error terms, for example testing for their white noise character, or any such test would be done on mu-t. So to summarize, in the deterministic non-stationarity, all we need to do is model out the time trend and then work on the residuals. Please remember, we have studied two kinds of non-stationarity, stochastic and deterministic. If you perform the treatment which is not or opposite, for example, if you perform the treatment of deterministic non-stationarity on stochastic non-stationarity, for example, if it is stochastic non-stationarity and you add time trend, or vice versa, on deterministic non-stationarity you take first difference, then the resulting process or the resulting model will not be error free, it will be inefficient, and most probably the non-stationarity will not be removed. So it is better to first understand what kind of non-stationarity is causing the stochastic or deterministic trend, and then accordingly treat this process in a different manner. In this video, we'll conduct the time series and stationarity properties, try to distinguish between different processes through visual examination. Let us first look at this white noise process with the zero mean. Notice how frequently this process fluctuates around its mean. It quickly comes back and forth around this mean. So this characterizes the white noise process with a zero mean. Next, let us look at a random walk, a process which has a unit root, and a random walk process with a drift. Notice the process with a random walk, this random walk process, whenever it deviates from its mean, it deviates much further away for longer times as compared to the white noise process. Similarly, when we add a positive drift to it, the purple process, it deviates on the positive side much frequently. You can think of a process with negative drift also going in a very similar fashion on the opposite side. So a random walk process with a positive drift is expected to deviate much further from its mean on the positive side, while a negative drift will go much ahead on the negative side. Next, let's look at a deterministic trend process. Now, while this process fluctuates a lot like a white noise process, but it fluctuates around that deterministic trend. So it fluctuates very frequently around that deterministic trend. If we detrend the process, if we detrend this process, the residuals from the process will fluctuate like this, because once the trend has been removed, it becomes very close to a white noise process. Lastly, let us examine three kinds of autoregressive process, one with zero autocorrelation, which is closer to what we call as white noise, one with a higher 0.8 autocorrelation coefficient, and another process with the autocorrelation coefficient of 1. So these are first order autocorrelation coefficient. Let's see what kind of processes result from these correlation. Notice the process with autocorrelation coefficient of 1, which is of course a sort of unit root process or random walk process. The process deviates a lot from its mean, and that too much further away. Any shocks to the system would persist a much longer in this kind of process. While if we compare it with the 0.8, which is this dotted pink line, that also deviates, though relatively less as compared to 1, but still deviates as compared to a process is phi equal to 0, where the deviations are much less and they are fluctuating around the mean, which is almost as if the white noise process. Now, to summarize this video, we studied that and we saw visually that a white noise process has no trending behavior and it frequently crosses its mean value, which is generally 0. We also saw the random walk process and a random walk with drift process, and they exhibited long swings around their mean value, and they cross their mean value very rarely as compared to the white noise process. We also saw, when we compared these two, random walk and random walk with drift, we found that the positive drift, if in the process there was a positive drift, the series was more likely to rise over time and deviate much further as compared to a simple random walk. And this effect of this positive drift became greater and greater as the time passed. Similarly, we can think of negative drift as taking process on the negative side of the mean, on the lower side of the mean. Lastly, we also recall that we saw visually the deterministic trend process, and we noted that it does not have a constant mean, but those fluctuations, they were around the upward trend. So the mean was sort of increasing secularly upward, and those fluctuations in the deterministic trend process were around that upward trend. And if this trend were to be removed from the series, a plot very similar to white noise process would be obtained. In a series of next few videos, we'll try to understand test of non-stationarity, or what we often call as unit root test. To begin with, let us understand with the help of a simple Dickey-Fuller test of non-stationarity. We start with the simple autoregressive model, which is yt equal to phi times yt minus 1 plus mu t, which is a first order autoregressive model. The test of non-stationarity here is a simple basic objective to test whether the null hypothesis that phi here is equal to 1. We are not testing phi greater than 1 because those cases will result in explosive process which are generally not found in economics and finance. So by default, the alternative is phi equal to 1, and the only one-sided alternative becomes phi less than 1 because we are ignoring phi greater than 1. So we formulate our null hypothesis that series contains a unit root, which means phi equal to 1, and alternative, the only possible one-sided alternative is that H1 is series is stationary. Now, because the formulation of this kind of equation, there is a possibility that phi equal to 1 and estimation of then this kind of model will not be feasible. So we transform this model a little bit by subtracting both sides from yt minus 1, both LHS and RHS. And then this yt minus 1 will become delta yt because of first differencing, and the right side will become psi times yt minus 1 plus mu t, where psi is nothing but equal to 1 minus phi because of that subtraction with yt minus 1. So the resulting equation, that is delta yt, which is the first difference of yt, equal to psi times yt minus 1 plus mu t. So an equivalent test of phi equal to 1, which is the null that process stationary, is equivalent to test of psi equal to 0 because psi is nothing but phi minus 1. Here, because we are ultimately subtracting yt minus 1 minus yt minus 1, which results phi minus 1 as coefficient. The question is, why not use this original regression? Because original regression, obviously, by the null hypothesis of being non-stationarity, and if you are going with the null and estimating this kind of model with phi being 1, that is not econometrically efficient, and all those problems of spurious regression will follow. Now, generally in this process, we assume in financial market returns there is no drift or deterministic trend, but let's say you believe you want the model to be very generalized kind of model to test for non-stationarity, that is by allowing a drift or intercept along with the deterministic trend. Then you can consider a model like this, where in addition to this phi into yt minus 1, you also introduce mu, which is the drift. It can be positive or negative drift, and a deterministic trend through t. So this will take care of your deterministic non-stationarity as well. Now again we repeat the same step. We subtract by yt minus 1. So we get delta yt equal to psi times yt minus 1 plus mu plus lambda t plus mu t. So this is a more generic expression where delta yt is nothing but yt minus 1. And then we test this model for non-stationarity. So a test that is non-stationarity, which means phi equal to 1, and alternate if null of non-stationarity is rejected, then process stationary with phi less than 1. Equivalent model here, psi, then psi, you test null with psi equal to 0, and alternate becomes that psi is less than 0, where psi is phi minus 1. So this again is a test of random walk against a stationary AR1 with drift and time trend. Why drift and time trend now? Because we have included these two terms. Now, unlike the original model where we would have tested in a model like yt equal to psi times yt minus 1 plus error term, we would have tested phi for its significance with phi, the t value as phi upon standard error of phi. Because these are estimates, we put a hat symbol. But now because we have transformed the model and the resulting coefficient psi is tested, and these are called tau tests. Why these are called tau tests? Because these are not your regular regressions. There is a possible non-normality in the process. There is a possibility of that. So the corresponding test statistic for psi is not the regular t statistic. It is different. We call it tau test, and the value of tau, its notation is similar, which is psi hat, estimated value of psi upon standard error of psi, but the distribution is not similar to t. So the distribution is very different, and it is provided through simulations, and it has been found that it is different from t. In fact, this tau is slightly higher in values as compared to our conventional t values, that means it requires more evidence. If you study more about the t distribution and evidence in models, you will find that t tau being higher reflects more evidence is required to reject the null. So these tau are rather non-standard, unlike the conventional standard t distribution. And like I said, because we are rejecting the null when psi is less than 0, which means psi minus 1 is less than 0, or psi less than 1. In other words, the tau values corresponding to this alternate hypothesis are larger, negative. In terms of magnitude, they are larger than the regular t-stat. That means they are larger negative, because we are looking at negative values to reject the null. And essentially, in economics and finance sense, these larger tau values indicate that we are requesting for more evidence while rejecting the null of non-stationarity. To summarize this video, here we saw the construction of simple Dickey-Fuller or DF test of non-stationarity. In the next set of videos, we'll augment this test and study augmented Dickey-Fuller test and few other tests of non-stationarity and how to use them in inferring whether a process is stationary or not.